A very good morning, students. Welcome to the lecture series on operating system. In this session, we are going to discuss about preemptive scheduling algorithms. As a part of the preemptive scheduling algorithms, shortest remaining time first scheduling algorithm and round robin scheduling algorithms will be discussed. Coming to the preemptive scheduling algorithm, if the CPU is executing a low priority job during the same time, if any high priority job has entered into the main memory, then immediately before the completion of the execution of the low priority job, the CPU will be switched to high priority job. Then it is referred as a preemptive versions of the scheduling algorithm. So firstly, we are going to discuss about the shortest remaining time first scheduling algorithm. This shortest remaining time first scheduling algorithm is referred as a preemptive version of shortest job first scheduling algorithm. Okay, shortest job first scheduling algorithm is a priority scheduling algorithm, right? How do we say that it is a priority scheduling algorithm? The priority can be assigned based on the lowest CPU burst time, right? So it is a preemptive priority scheduling algorithm, right? Like a preemptive priority scheduling algorithm. Thereafter, here the processor is going to be allocated to a process which is having closest CPU execution time. Means, for example, P1 is a process which is having 2 seconds of time to complete its execution. P2 is another process which needs the CPU for 5 seconds. Then who is going to get the CPU at first? P1, because P1 is having a closest time to the completion. So the process P1 is going to get the CPU at first compared to the process P2. And implementation of the shortest remaining time first scheduling algorithm is comparatively difficult than the other scheduling algorithms. Why? Because we could not able to notify the required CPU burst time for the execution of a process in the interactive systems. So if we could not able to notify the required time for the completion of the execution, then the implementation becomes very much difficult. So in the case of the interactive systems, that design and development of shortest remaining time first scheduling algorithm will be highly difficult. And then it is followed in the case of the batch environments. Means if any of the processes which are having the similar kind of the requirement, those kind of process will be followed in the under shortest remaining time first scheduling algorithms. And thereafter, this particular algorithm has been developed by considering the arrival times also. So the processes which are arriving into the main memory according to their priorities, automatically CPU will be switched from one process to another process. Means according to the priority and according to the arrival time, the switching of the process from the switching of the CPU from one process to another process will be carried in the case of the shortest remaining time first scheduling algorithm. Let us solve some problems on the shortest remaining time first scheduling algorithms also. Guys, you have been given with 4 processes called P1, P2, P3, P4. In addition to that, you have been given with 2 more informations called arrival time and CPU burst time. What is arrival time? The time of the time at which the process has entered into the main memory is referred as an arrival time. Okay, which of the process has arrived into the main memory at first? P1 has arrived at 0 second. Means P1 is the first process which entered into the main memory at first. Then P2, then P3, then P4. Likewise, this is the order of allocation of the CPUs. But in addition to that, we need to consider the CPU burst time also. Okay, so by considering the arrival time and the remaining CPU burst time, we are going to allocate the CPU for each process. Okay, students, we are going to construct the Gantt chart for this given problem using shortest remaining time first scheduling algorithm. Okay, first of all, who is going to get the CPU at first? P1 is going to get the CPU for 0 seconds. At 0th second, P1 is going to get the CPU. For how much of time? Because the next process has entered into the memory after 1 second of time. So, I need to assign the process. I need to assign the CPU for this process for 1 second only. So, I am going to assign the CPU for process P1 for 1 second only. After 1 second of time, what are there in the main memory? What are there in the main memory after 1 second? P0 and P1 are there in the. After 1 second of the time, there are 2 processes in the main memory. What are those 2? One is P1 and other one is P2. What is the time requirement of the process P1? P1 needs a CPU for 8 seconds of time, but already 1 second was assigned. So P1 needs a CPU for 7 seconds. What about the P2 process? P2 needs the CPU for 4 seconds of the time. So which of the processes is having the lowest CPU burst time now? Now P2 needs the lowest CPU time compared to the process P1. So I am going to assign only 1 second of time for process P2. P2 is assigned with 1 second for CPU. Okay, after 1 second, another process is coming into the main memory. What it is? It is a P3. P3 is getting into the memory and which is also having the CPU burst time as 9 seconds. What about process P2? P2 has been assigned with 1 second, right? So P2 needs the CPU for 3 seconds only. What about process P1? P1 needs the CPU for 7 seconds. Now which of the processes having the lowest CPU requirement? Now the process is identified as P2 again. So P2 is going to be assigned with the CPU for 1 more second. Okay, after 1 more second of CPU assignment, the requirement of the CPU for process P2 is changed to 2 seconds and P1 requirement is 7 seconds and P3 requirement is 9 seconds, right? Now, which of the process has entered into the main memory now? After 1 second, another process has entered into the main memory, that is P4. And what is the CPU requirement of the process P4? Which is 5 seconds. Within the 7295, which of the process is having the lowest CPU burst time? That is P2 itself. So P2 is going to be assigned to CPU for 1 more second. Okay, after 1 more second, does any other processor coming into the memory? No. So continuously I am going to assign the CPU for 1 more second also. After 5 seconds, the process P2 has completed the execution. There are no other processors coming into the main memory. Based on that, now onwards the process is going to be considered as a shortest job first scheduling algorithm. Once all the processes have entered into the main memory, then the difference between the shortest remaining time first and shortest job first once after arrival of all the processes into the main memory, there will be no specific difference between the shortest job first scheduling and the shortest remaining time first scheduling algorithm. Based on that, I am going to assign the CPU for P4 process at next. P4 process is going to be assigned with the CPU for 5 seconds, means 5 to 10, right? Then which of the process is going to get the CPU at next? Next, immediately I am going to assign CPU for process P1. P1 is going to assign the CPU for 7 seconds. After 17 seconds, the execution of the process P1 will get complete. Then immediately I am going to assign the CPU for process P3. P3 is going to be assigned with 9 seconds, means 26 seconds. Okay, after 26 seconds of time, after 26 seconds of the time, all processes have completed the execution. Okay, now let us redefine the Gantt chart as like, firstly P1 has been assigned with the CPU for 1 second, then P2 got the CPU for 4 seconds, then P4 got the CPU for 5 seconds, then P1 got the CPU for 7 seconds, and then finally P3 got the CPU for 9 seconds. After 26 seconds of the time, entire all process have completed the execution. Now I am going to compute the average waiting time, average response time and average turnaround time as like the earlier problems. Coming to the process P1. When does process P1 got the CPU? P1 got the CPU initially for 1 second, right? And after that, it has completed the execution after 17 seconds and it got the CPU after 10 seconds, right? So up to 10 seconds it is waiting, right? Up to 10 seconds it is waiting, but within those 10 seconds only 1 second it is getting executed, right? So 10 minus 1 is the waiting time of the process P1. Coming to the process P2. P2's waiting time is 1 second. But when does it was admitted into the main memory? Only after 1 second, right? So even though it is waited for 1 second, but unfortunately it has came into the main memory only after 1 second. So the waiting time is 1 minus 1, it is 0 seconds. What about the P3 process? P3 process waiting time is 17 seconds, but it came into the main memory after 2 seconds only. So 17 minus 2, which is 15 seconds. What about the P4? P4 got the CPU after 5 seconds. What about its waiting time? Its waiting time is 5 minus 3, which is equivalent to 2. So average waiting time is 6.5 milliseconds. Okay, but in the case of the preemptive scheduling algorithms, not like in non-preemptive, the response time and waiting time should not be equal. In the case of the preemptive, the response time and waiting time should be different only. So I am going to recompute the average response time here. What about the process P1? P1 got the first response, right? So it doesn't wait for the CPU. So the response time of the process P1 is 0 second. When does process P2 got the CPU? P2 got the first response at 1 second. How much of time it has waited for the CPU? It doesn't wait. It means only after 1 second only it has arrived, right? So the response time is 1 minus 1, which is 0 second. Thereafter, what about P3? P3 got first response after 17 seconds, right? 17 minus 2. Why I have written it 2? Because it has arrived into the main memory after 2 seconds of time. So 17 minus 2. Coming to process P4. P4 got CPU after 5 seconds of time, but it has entered into the memory only after 3 seconds. So the response speed is given after 5 minus 3 seconds, means it has waited for 2 seconds only. So on overall, the average response time is 17 by 4, which is equivalent to 4.25 milliseconds. Likewise, the turnaround time is also computed for the given problem. Students, you have been given with a small example. You are requested to compute the average turnaround time, average response time and average turnaround time for the given problem using shortest remaining time first scheduling algorithm. Here the processes are P1, P2, P3, P4 and P5. The arrival times are 0, 1, 2, 3, 4 respectively, and the CPU burst times are 8, 6, 1, 9, 3 respectively. We can construct the Gantt chart. According to the Gantt chart, you can compute the waiting time, response time and turnaround time for each process. Okay. First of all, which of the process has entered into the memory at first? The process P1 has entered into the memory at first. Okay. So P1 is going to be assigned with the CPU at first, right? So I have at 0th interval of the time 0, 1, 2, 3, 4. I have 4 splits. At the 0th interval, only process P1 is there in the memory. After 1 second, there are 2 processes P0, P1. After 2 seconds, there are 2 processes. There are 3 processes called P1, P2, P3. After 3 seconds, there are 4 processes P1, P2, P3, P4. After 4 seconds, all 5 processes are there in the main memory, right? So firstly, at 0th second, there is no alternative. So firstly, I am going to assign the CPU for process P1 only. For only 1 second. Okay, after 1 second. After 1 second, I have 2 processes in the main memory. What are those 2 processes? One is P1 and other one is the P2. What about the CPU burst time of P1? P1 needs the CPU for 7 seconds. Why? Actually, it is having 8 seconds as a requirement, but already 1 second was assigned to it. So it has been left with 7 seconds of time. Then what about P2? P2 needs the CPU for 6 seconds. Within these 2, which of them is smaller number? That is a P2. So P2 is going to be assigned with the CPU for 1 second. Okay. Now the CPU burst time of the P1 has not been changed because we have assigned CPU for process P2. So its time requirement was changed to 5. P1 CPU burst time is 7 and P3's CPU burst time is 1. Means who is going to get the CPU now? P3 is going to get the CPU. P3 has been assigned with the CPU for 1 second. Now, within the 1 second, the process P3 has completed the execution, right? Because it needs the CPU for only 1 second. So P3 has completed the execution. What about the required CPU burst times now? P1 needs the CPU for 7 seconds. P2 needs the CPU for 5 seconds. P4 needs the CPU for 9 seconds. Now, which of the process is having the lowest CPU burst time? That is P2. So P2 is going to get the CPU for 1 second. For 1 second. After that, what about the CPU burst times? 7 seconds for P1, 4 seconds for P2. P3 has already completed. What about P4? P4 needs the CPU for 9 seconds. What about P5? P5 needs 3 seconds. Now what is our consideration? All other processes are there in the memory. If whenever all processes are there in the memory, then the shortest remaining time first scheduling algorithm and shortest job first scheduling algorithm will serve like similar only. So which of the process is going to get the CPU fast? Now the process P5 is going to get the CPU. Why? Because P5 needs a CPU for only 3 seconds. So 3 plus 4 plus 3, that is equal to 7 seconds. Then finally P2 is going to get the CPU for 4 more seconds. Then P2 has completed. Finally we have been left with 2 more processes. One is P1 and other one is P4. P1 needs a CPU for 7 seconds. For 11 plus 7, which is equivalent to 18 seconds. Now P1 also completed the execution. Finally we have been left with only P4, and P4 needs a CPU for 9 seconds. This is the way we need to compute the Gantt chart for the given problem. So here I can able to identify P1 fast, then P2 got the CPU, then immediately P3 has got the CPU, then P2, then P5, then P2, then P1, then P4. Likewise, we have assigned the CPU from one process to another process. During the execution also, if any high priority job has came into the memory, then immediately we have switched the CPU from that low priority job to high priority job. Now, let us talk about the another kind of a preemptive scheduling algorithm called round robin scheduling algorithm. Okay students, this round robin scheduling algorithm is highly referred in the case of time sharing machines. What about the time sharing machines? In the case of the multitasking machines or in the time sharing machines, the response time is a criteria to evaluate its performance. So, in any of the machine where the response time is highly essential, is all such a kind of machines, this round robin scheduling algorithm is preferred. Here, the CPU will be switched from one process to another process once after the completion of the fixed amount of the time. The fixed amount of the time is also called as time quantum or time slice. So, expiration of the time slice, immediately after the expiration of the time slice, CPU will be switched from one process to another process. Okay, that what is the other name of that particular time slice? It is also referred as a time quantum. And then this here the ready queue is referred like a circular queue, because every process has entered into a queue in the case of the FIFO or shortest job or shortest remaining time first scheduling algorithms. But in the case of the round robin scheduling algorithm, the ready queue will be treated like a circular queue. Thereafter, the CPU scheduler will be around the ready queue for the allocation of the round robin scheduling algorithm is implemented when the ready queue is kept like a circular queue, and then this queue is also expected to be first in first out, and then the process which is just entered into the main memory, means the new process has been kept at the tail of the ready queue, and the process which is located at the first of the ready queue will get the CPU. Means the CPU scheduler will always take a process which is held at the first location of the circular queue. Then coming to the execution of the round robin scheduling algorithms. Here every process will be allocated for a time slice, means a small interval of the time. Within that small interval of the time, the process may complete the execution, or else some of the times the process could not able to complete the execution within the given small interval of the time. Then the process will be moved back to the ready queue itself, and then it will be allocated with the CPU after some time. Okay, so within the given interval of the time, there is a possibility to complete the execution. Otherwise, it may keep on continuous execution by giving the interrupt. Hope you remember about the scheduler dispatch in the case of the process state diagram. In the process state diagram, with the scheduler dispatch, the process has moved from ready state to running state. And when the interrupt was given, then the process has moved from running state to ready state. And during that time, I have clearly mentioned you guys that in the case of the time sharing machines, there is a possibility of having an interrupt based driven system. During that, the process will be moved from running state to ready state. This is the example scenario. In the round robin scheduling algorithms, there is a possibility to transit a process from running state to ready state. Once after expiration of the time slice or a time quantum, the process will be automatically moved from running state to ready state. If any of the process which is having the higher CPU burst time, then that process is going to be kept in the memory for long amount of the times. Thereafter, it is highly required to know about the problem of the round robin scheduling algorithm. In the round robin scheduling algorithm, if the time quantum was kept as very minimum, then more number of the context switches will rise. What is the meaning of the context switch? Saving the state of the one process and reloading the state of the other process is referred as a context switch. This context switch is surely increases the overhead over the system. So this kind of problem will raise if we are keeping the time quantum as very minimum. Okay, students, we are going to solve a problem on round robin scheduling algorithm. Firstly, there are three processes named P1, P2 and P3 with the CPU burst times as 24, 3 and 3 respectively, and I have considered the time quantum as 4 milliseconds. Okay, means for every 4 milliseconds the CPU is going to switch from one process to another process even though it has not been completed. Okay, please remember that point. Which of the processes came into the main memory at first? P1 has get into the main memory at first. So firstly, P1 is going to get the CPU for 4 seconds only. Okay, why have I assigned 4 seconds? Because I am going to assign 4 seconds, and what about the CPU burst time? It is 24 seconds. The minimum time is going to be assigned. Which is the minimum? 4 seconds is minimum than 24 seconds. So 4 seconds is going to be allocated for the process P1. Then which process is going to get the CPU at next? Immediately the CPU is going to be allocated for process P2. What is the CPU burst time of the process P2? Which is 3 seconds. And what about the time slice, which is 4 seconds? So compared to 4 seconds, the CPU burst time is lower. Due to that reason, the process is going to be allocated with the required CPU burst time, that is 3 seconds. So 4 plus 3 seconds, which is equal to 7 seconds. After 7 seconds of the time, the CPU is getting moved from process P to P3. The same condition, P3 needs the CPU for 3 seconds and the time slice is 4 seconds. Again, the CPU burst time is lower than the CPU time slice. Due to that reason, process will be executed for the CPU burst time instead of the time slice. Because if you have given the time slice 1 second of time, the CPU is getting idle. Due to that reason, instead of to avoid the keep the CPU as an idle, we are going to assign only CPU burst time if it is lower than the time slice. So P3 is going to be assigned with 3 seconds of time, and after 10 seconds, first slice P1 is assigned with 4 seconds, then P2, then P3. But within the time slices, P2 and P3 has completed the execution. Only P1 needs a CPU. How much of time P1 needs a CPU? Initially it needs a CPU for 24 seconds, right? But 4 seconds were assigned. Means it has been left with the requirement of 20 seconds. But I have assigned only 4 seconds, right? Next, immediately I am going to assign 4 more seconds. Then, any other process are left in the main memory? No. So I am assigning only P1 with 4 seconds, 4 seconds, 4 seconds. Finally, another 4 seconds was assigned. With this, the execution of the process P1 got completed. Okay. If no other process are being left, then only CPU will be assigned to that process only. Okay. Now, let us talk about the average waiting time. Guys, let us talk about the waiting time. What is the waiting time of the process P1? Here is process P1 is waiting? No. Means its waiting time is 0 seconds. Here process P1 is waiting, right? 3 seconds. Here process P1 is waiting, right? So, what is the total waiting time of the process P1? 6 seconds. What about the process P2? P2 has waited up to 4 seconds of time. After 4 seconds of the time, process P2 got the CPU. So, the waiting time of the process P2 is 4 seconds. What about process P3? P3 has waited up to 7 seconds of time. Coming to the waiting time of the process P1. The process P1 is waiting here, right? So process P1 is not waiting here, right? So, remove everything. Okay, let us calculate here after. Coming to the waiting time of the process P1 can be computed now. Firstly, CPU is assigned to process P1. Means CPU is not waiting here. So the waiting time of the process P1 is assumed as 0 here. Coming to P2 here. P2 here, P1 is waiting, right? So the waiting time of the P1 is 3 seconds. Here P3 is executing, means P1 is waiting. So P1 is waiting for 3 more seconds here. On total, P1 is waiting for 6 seconds. Now let us check about P2. Here P1 is executing, means P2 is waiting. So P2's waiting time is 4 seconds. What about P3? Here P1 is waiting, means P3 is waiting. What about its waiting time? 4 seconds. Plus, here P2 is executing, means P3 is waiting, means 3 seconds. Means a total 7 seconds. This is the 7 seconds waiting time. So, what is the average waiting time? 6 plus 4 plus 7 whole divided by 3, which is 17 by 3. 5.67. Let us compute the average response time. Average response time. What about the average response? When does the process P1 got the first response? Only after 0 seconds, right? So after 0 seconds, P1 got the first response. So 0 plus. When does P2 got the first response? After 4 seconds. When does P3 got the first response? After 7 seconds. So 0 plus 4 plus 7 whole divided by 3, which is equal to 11 by 3. Equal to 3.67. Okay, so average response time is 3.67. Now let us check about average turnaround time. Average turnaround time is about process P1. When does process P1 has completed? 30 seconds. When it was submitted? 0 second. So 30 minus 0, 30. Plus, what about P2? P2 has completed after 7 seconds. P3 has completed after 10 seconds. Whole divided by 3. 47 by 3. Which is equal to 15.67. Okay students, this is the way we are supposed to compute the average turnaround time, average waiting time and average response time for a given problem. I have given a small exercise problem to you and we can solve this problem also. Guys, before going to discuss about another problem, here a small discussion is given. Like in the case of the round robin scheduling algorithm, if the time quantum is too high, then round robin scheduling algorithm just behaves like a first come first serve scheduling algorithm. Okay, so you could not able to find any kind of difference between first come first serve scheduling algorithm and round robin algorithm if the time quantum is too high. Likewise, if you keep the time quantum as very small, then the number of the context switches will be very high. If the number of the context switches are more, then the CPU will take more amount of the time for switching of the CPU from one process to another process. Means instead of getting the higher efficiency, most of the time CPU will be in a process to move from one process to another process. So efficiency of the CPU will be fall down if you are keeping the time quantum as very small. Let us take a small example. For example, a process is there whose process time is 10 seconds. I have considered the time quantum as 12 seconds. So, CPU burst time is 12 seconds and the process CPU burst time is 10 seconds. Means there will be no case of any context switches. So, once the CPU has been allocated to that particular process, it completes the execution. So, there is no question of any context switch. Now, I have reduced the time slice. What about the time slice now? The time slice has been changed to 6 seconds. What about the CPU burst time? 10 seconds. Is the 10 is less than 6? No. Means the CPU is going to be allocated for the process P1 for 6 seconds only. Okay, once after that, again the CPU is going to be allocated for that particular process. Okay, means there is a context switch for one time. In the case of the CPU, in case of time slice as 6 seconds. But when the time slice has been changed to only 1 second, means for every 1 second there is a transition. Okay, so there is a transition, there is a transition, there is a transition. Likewise, the CPU has been switched from one process to another process for 9 number of the times. So the number of context switches will be 9 in this scenario. So what is the general observation? If the time quantum has if the time quantum has been reduced, the number of the time slices, the number of the context switches are getting increased. Okay, so time quantum is indirectly proposed to context switches. What is the meaning of this? If the time quantum is small, then the number of context switches will be high. If the time quantum is high, the number of the context switches will be low. This is the consideration. Okay students, so now we have been given with another practice problem. We have been given with 4 processes called P1, P2, P3, P4 with the CPU burst times as 4, 3, 5, 3 respectively. We need to compute the average waiting time, average response time and average turnaround time for the given problem using round robin scheduling algorithm. Consider the time quantum as 2 seconds. Means every process have a CPU for only 2 seconds. After 2 seconds of time, immediately the CPU is going to be switched to another process. Okay, so firstly, which of the process is going to get the CPU? Process P1. P1 is going to get the CPU for only 2 seconds because the CPU burst time of the process P1 is 4 seconds and I am going to assign the time slice is 2 seconds. Which of them is small? 2 seconds is small. So P1 is going to get the CPU for only 2 seconds. After 2 seconds, immediately CPU is going to be assigned for P2 for 2 seconds only because P2 needs the CPU for 3 seconds and CPU is allocated for the process P2 for 2 seconds. Now it is very clear that the CPU burst time of the process P2 is more than the time slice. Due to that reason, again the process P2 is going to get the CPU for 2 seconds only. So P2 got the CPU for 2 seconds. So after 4 seconds, P3 is going to get the CPU for 2 more seconds. Then P4 for 2 seconds again. Okay, after 2 seconds of CPU allocation, it has been changed to 2, 1, 3 and 1. Now, second round of allocation. In the second round of allocation, P1 is going to get the CPU for 2 seconds only, right? After that, P2 needs the CPU for 1 second, but the time slice is 2 seconds, which is need to be assigned only 1 second because if you have assigned 2 seconds, CPU sits idle for 1 more second, right? So P2 is going to be assigned with the CPU for 1 second only. Then P3 is going to be assigned with the 2 more seconds because it needs the CPU for 3 seconds, right? Thereafter P4 for 1 second. Then finally we are going to assign P3 for 1 more second. After 15 seconds of time, all processes have completed the execution. Okay students, hope you are very much clear about the computation of the average waiting time, average response time and average turnaround time. Firstly, I am going to compute the waiting time, response time and turnaround time for all these processes. Coming to the waiting time, when does process P1 has completed? After 10 seconds. Okay, keep an eye on this number. Okay. Firstly, P1 is executing, means that here it is not in waiting state, here it is in waiting state, here it is in waiting state, here it is in waiting state, means that totally 2 plus 2 plus 2, it is 6 seconds. Okay, what about the process P2? Process P2 has completed the execution here, but here the process P2 is executing, therefore there is no question of waiting. So here the process P2 is waiting, right? Here process P2 is waiting, here process P2 is waiting, here process P2 is waiting. Here 2 seconds, plus 2 seconds, plus 2 seconds, plus 2 seconds. On total, it is waiting for 8 seconds of time. Sorry, 8 seconds of time. What about process P3? What about process P3? P3 is waiting and it has been completed at last. After 15 seconds of time, it has completed the execution. What about the CPU burst time of the process P3? P3 needs a CPU for 5 seconds of time. So 15 minus 5, which is equal to 10 seconds. So the waiting time of the process P3 is 10 seconds. Initially, I have given the basic definition of the waiting time. What is the basic waiting time definition? That the completion time minus CPU burst time. When does process P3 has completed? After 15 seconds. What about the CPU burst time of the process P3? 5 seconds. So complete all other time, it is in waiting state only. So the waiting time of the process P3 is 10 seconds. Thereafter, I am going to compute the response time. When does process P1 got the first response? At 0th second. What about P2? P2 got the first response after 2 seconds. When does P3 got the first response? After 4 seconds. Coming to the turnaround time. When this process P1 has completed? It has been completed after 10 seconds. What about P2? P2 has been completed after 11 seconds. What about P3? P3 has been completed after 15 seconds. I am going to compute the average waiting time as 6 plus 8 plus 10. The average waiting time is 6 plus 8 plus 10, which is equal to 24. 24 by 3 equal to 8 seconds. What about the average response time? Average response time is 0 plus 2 plus 4. It is 6 by 3 equal to 2 seconds. Coming to the average turnaround time. Average turnaround time is 10 plus 11, 21. 21 plus 15, 36. 36 by 3 equal to 12 seconds. Okay students, hope you are very much clear about the round robin scheduling algorithm also. This is the end of our scheduling algorithms. Both uniprocess scheduling algorithms includes preemptive scheduling algorithms. Thank you students. This is the end of the scheduling algorithms. So far we have discussed about preemptive scheduling algorithms and the non-preemptive scheduling algorithms. In the case of the preemptive scheduling algorithms, we have discussed the shortest remaining time first scheduling and the round robin scheduling algorithms.